Yung second part ng lecture natin, relatively mas kaunti na yung content. I'll just show two algorithms for the sorting problem. Yung analysis of algorithms dito is meant to be an introduction kay Cormen. Hindi pa siya nagpakita ng much details on how to actually compute for the running time of the algorithms in terms of yung mga different notation. Pero nagpapakita na siya ng idea how we can get the running time analysis of an algorithm. Parang simple example for one that is an iterative algorithm, which is yung insertion sort, and then one na recursive yung form ng algorithm, and then how we can compute for the running time if recursive yung algorithm. So yeah, so dito sa CS210, I am planning to use Levitin and Cormen ng side by side kasi maganda din na makita how they attack yung certain concept differently. May mga concepts na okay for me gamit ang Cormen. May mga certain concepts like, for example, better for me si Levitin in terms of explaining how to compute for analyzing algorithms basically. Medyo mas intuitive for me yung Levitin. So, I will use both. Depende sa kung ano yung mas nakikita ko na better or chewable yung content. Sometimes kasi si Cormen hindi ganun ka-specific in terms of how they get it. Parang ina-assume niya na nag-gets na ng mga students. So, hindi ko siya masyadong gusto on that note. So, yeah. So, for this lecture, ang gagamitin ko is a Cormen slide. This is the first lecture actually nung Cormen pwedeng ginamit din sa CS125 before. Okay. So, etong initial parts is similar to the rationale why it's important to analyze algorithms katulad nung naunang lecture 1.1. But dito, instead of analysis of algorithms, chinek din niya why is it important to check for computer program performance. So aside from the algorithms performance, yung computer program performance, may mga other metrics how to say that your computer program is good. So sometimes yung modularity is a factor. If it is user-friendly, ito yung mga other factors na pwede din na i-consider aside from the running time of an algorithm. Yung simplicity, extensibility, reliability, more on computer program to at hindi yung algorithm, no? So functionality, robustness, and maintainability. This is on a more practical reason why important din yung mga other factors na to aside dun sa running time of the algorithm na ginagamit ng computer programs. So, why do we need to study algorithms and performance? Because it helps us to understand yung scalability. So, sa pag-analyze ng algorithm, we can identify na if we have this input and ganito na kalaki yung input natin, kakayanin pa ba nung algorithm natin now? If we go from n equal to 10 to billions or millions, so we can have a gauge kung kailan tayo magpapalit ng underlying algorithm. If it's no longer scalable when we go to actual value of n na medyo malaki na. Performance often draws the line between what is feasible and what is impossible. Algorithmic mathematics provide a language for talking about program behavior. So, this is the parang formalization ng mga program behavior. And then, performance is necessary because it's the currency of computing. In fact, hindi siya but it's sometimes currency talaga siya ng computing because we pay for computing resources, diba? So the more energy na kailangan for the computer to run, may actual cost. The total number of pods na gagamitin natin, for example, in AUS or in GCP, may cost yun and so on. The lesson of program performance generalized to other computing resources. And it's important to study algorithms because we want to get an algorithm na mabilis because speed is fun. Okay? So let's go back to the problem of sorting. Problem, again, is composed of two parts, the input specification and the required output. And as mentioned a while ago, dapat yung manner how we define yung input is it is well defined, kumbaga, and mathematical yung form. For the output specification for the sorting problem, it's a permutation such that this is true. So for example, we have an instance of the input 824936 and the required output for the sorting problem is this one. Okay, so to say that this is a legitimate output for the given input, kailangan yung output niya ay tama. Okay, so, or nag-o-obey yung output na to dun sa specification na na-define dun sa output. Okay, so may existing algorithm for this problem. It's called insertion sort. So this is an iterative algorithm. It's not a recursive algorithm. Ang main idea is to identify a key doon sa input natin na sequence of numbers, and then ililipat natin yung particular key na yon dun sa tamang posisyon. And we do that for all items in this array from j equal to 2 to n. So parang nag-i-increase yung iterator natin j 2 to n, and then we identify yung correct position ng bawat element na yon dun sa array. Okay? So yung ginagawa nung yung pag-identify ng right position is what's happening dito sa part na to ng pseudocode. So to give you an idea how it computes, meron tayong sorted part ng array. And then, this is our key. What we can do is to compare yung item, yung element na nasa AJ, and compare it to the parang sorted part of the array, and then we insert it to the correct position, starting from the rightmost to the leftmost. Okay, so ito lang yung ginagawa ng part na to. And then then every time naglalagay tayo ng content dito sa nasa left side of the array, every time itong part na to is tama yung positioning. Okay? So, gagawin yan until makaabot tayo dun sa last position. And then at the end, magkakaroon tayo ng whole array na sorted na. Okay, so this is an example of insertion sort. Initially, this is the sequence na hindi sorted in increasing order, di ba? So, we start with j equal to 2. So, we have 2. And then we compare kung mas maliit ba si 2 kay 8. And then, since mas maliit si 2 kay 8, ililipat natin siya sa correct position. So, they will need to swap. Okay? So, j is equal to 2, j is equal to 3. Now, nito na tayo. We compare it dun muna sa pinakamalapit sa kanya, 8. Since 4 is less than 2, ililipat natin siya dito. Since 4 is greater than 2, then this is the correct position for 4. We do that for each position from j is equal to 2 hanggang sa j is equal to n, until maka-arrive tayo sa position na lahat ng mga items ay nasa correct in sorted order na. Okay? So the running time of the algorithm for insertion sort depends on the input. So kapag yung input natin is already sorted, for example, if ito na yung input natin, wala na masyadong swapping na mangyari. It's just a matter of parang getting from one position and then check, hindi ko na kailangang mag-swap and so on. So it's easier if sorted na yung input, but it's worse kapag kabaliktaran because you need to go through every comparison. Aabot siya hanggang sa dulo. Okay? So, that's the first criteria kung bakit mas matagal mag-run yung algorithm. The second criteria is with respect to the size of the input. So for this one, 1, 2, 3, 4, 5, 6, if we have 6 na n or total number of elements, mas mabilis mag-run ito compared if we have 100 items to sort or 1 million items to sort. So the running time is dependent on the size of the input. And then lastly, we seek yung upper bounds on the running time because everybody likes a guarantee. So what's yung upper bound dito is equivalent to getting the worst case. Gaano ba katagal pwedeng magtagal yung running time ng algorithm given any generic input size n. So may 3 kinds of analyses. Yung worst case analysis, average, and best case. Yung worst case analysis is usually done because this is the maximum time the algorithm will run on any input of size n. Dito, in fact, kino-consider yung worst possible input na pwedeng maging worst possible legitimate input for the problem. For the best case, ito yung best possible input for the problem. This is a cheat kasi hindi naman most of the time nangyayari si best case. And if we use the best case to say that this algorithm is good, hindi niya makikita yung ganitong cases, okay, na pwede mangyari talaga in reality. But sometimes, kinukuha rin yung tinatawag na average case analysis, and this is the expected time of an algorithm over all possible input of size n. May necessary information lang na kailangan before you can compute for the average case analysis, and that is ano yung statistical distribution ng input. So most of the time, yung ginagamit lang to compute for the running time analysis is the worst case analysis. Okay? Meron tinatawag na machine dependent time. So, yung relative speed and absolute speed, it depends on the parang actual speed of the computer, yung gigaflops, ganyan. Pwedeng in actual microsecond or seconds. However, para maging generic enough siya for different machines, we take into account yung total number of basic operation, the count of total number of basic operation. So we look at the growth of n as n approaches infinity. So the time is represented as a function of the input size. So ito yung tinatawag na asymptotic analysis. So regardless kung ano yung n, we can get an idea kung gaano katagal yung running time ng algorithm natin. Kasi kapag gagamitin natin to, lagi tayong magde-describe na for an input size na, let's say, 100 yung size, ito yung actual seconds. Sometimes ginagamit to for benchmarking siguro sa initial stages, pero for theoretical analysis, hindi yun enough. Yung ginagamit talaga is the asymptotic analysis, especially if you have a new algorithm to assess. So mathematically, may definition yung asymptotic notation. One possible notation na ginagamit is the theta notation. Ang ibig sabihin ng theta notation is that this function, yung actual running time of your algorithm is in theta of g of n if there exists some constants c sub 1 and c sub 2 such that it is bounded above and below by this approximation of this function. So we have a loose representation of the asymptotic growth of that function. So this is one possible representation of the asymptotic notation. Marami pang iba that I will discuss next week. We have small o and big O notation for this. In the engineering or more practical representation of the running time, we just ignore yung mga low order terms and we ignore the leading constant. For example, if we have this as the parang estimated na running time of the algorithm, represented in a function, sometimes we can just describe this function as g of n. And yung g of n dito is this one, n cubed. Okay? And this is obtained by dropping yung mga pinakamabababang low order terms like itong n squared and so on. And then we ignore yung mga constants like 95 and so on, and 3. So, this function is tinatawag din na in theta of n cubed because we can identify some c sub 1 and c sub 2 such that mapapakita natin na this statement is true for g of n na equal sa n cubed and for f of n na equal sa buong expression na to. Okay, so for the insertion sort, we have a worst case analysis of n squared. This is because we have parang j comparisons inside the loop, and we have the value of j na starting from 2 to n. So if you get the closed form of the arithmetic series ng j is equal to 2 to n ng in j time, yung kailangan natin i-compute, equivalent ito sa O of n squared or theta of n squared. May mas exact form itong value na to. And that is if you look at yun sa closed form ng sum of arithmetic series from 1 to n or from 2 to n. For the average case, I'll explain then kung how we can compute this one in the next lecture. But for the average case for insertion sort, nasa ganong running time din yung insertion sort. So regardless of any possible arrangement of the input, the expected running time of the algorithm is in theta of n squared. So it's good for small n but not for a very large n. Kasi imagine if you have 10, if n is equal to 10, let's say, ang number of times na yung insertion sort is 10 squared lang. But if you have 100 or 1 million, medyo matagal na. And ang question dun ay, may better algorithm pa ba aside from insertion sort? The answer actually is meron pa. So we have yung tinatawag na merge sort. Okay? So for merge sort, this is the pseudocode. We have a recursive definition of the algorithm. Ang ginagawa is, as an input, we have the whole set of sequence from 1 to n. If n is equal to 1, so if isa lang yung content ng array natin, then tapos na because trivially sorted na yung array or a sequence of element na isa lang yung content. Okay? And then, if hindi n is equal to 1, we recursively sort this array by dividing this array into two parts. The first portion that is from 1 to ceiling of n over 2 and yung the rest, which is yung kalahati pa na n over 2 plus 1 to n, yung parang tail end nung array. And then later on, we merge the two sorted list. So to get the recursively sort something, papasok ulit siya dito sa loob ng merge sort. And then para makuha yung sorted part ng array, kailangan niyang gawin ulit yung paghahati nito and so on. So this one is a recursive algorithm for sorting and may special na procedure to sort the to merge the two sorted lists. And ito yung tinatawag na merge na subroutine. Ang ginagawa sa merge na subroutine is if we have two sorted arrays, for example, this one is sorted 2, 7, 13, 20, 1, 9, 11, 12. Ang final na list will be a list containing all the elements ng two sorted array tapos in a sorted manner. At ginagawa yun by doing this. First, we have the parang two minimum elements ng array and then we obtain yung minimum between the two. So we have 1, and then check ulit 2 and 9, sinong minimum? 2, and then we have 7 and 9, 7, 9. Okay, so we are trying to merge two sorted array, and ang final output will be an array containing all of the elements. So the running time for merging the two array ay yung total number of elements na kailangan mong ilagay dun sa array. And ang running time nun is theta of n, or linear time. Okay? So, to analyze recursive algorithms, hindi na lang tayo nagka-count ng total number of times na umuulit yung iteration, but instead, we represent the algorithm into something na in recursive form din. So, parang we can get the running time of this algorithm by setting the total running time to be equal to t of n. So parang unknown pa sa atin yung t of n. T of n is equal to the time necessary for step 1. Assuming parang constant time lang naman to. And then yung step 2 dito, we represent it as the running time of solving this one or sorting this one, and the running time of sorting the next half. So, ang total running time nito will be the 2 times n over 2, because ang expected na input size na lang nung recursive part na pinasok mo dito is less. In fact, kalahati na lang. Okay, so we can represent this line as this line, 2 times n over 2. And then we have the third step as theta of n. So, kung meron tayong ganyang representation, we can actually represent it as a recursive formula na kapag n is equal to 1, we have this as the running time of the algorithm. Otherwise, if n is greater than 1, the running time of the merge sort is the time it takes to sort yung first half and yung second half. So that's 2 times t of n over 2 plus the running time of merging the two. Okay? So, itong part na to, actually, hindi ko din alam kung paano pa mako-compute eh. So, ang gagawin mo actually dyan is to treat yung n over 2 as n. And then you can identify na itong part na to, liliit ng liliit. And then we can finally count yung total number of steps necessary for merge sort if nakarating na tayo dito sa base case. And there's a visual representation of counting those number of steps. And yun ay kaya natin makita using a recursion tree representation. So, for example, unknown sa atin what is t of n, but for us to know yung t of n, what we can do for n greater than 1 is to compute for t of n over 2 na dalawang beses. Okay? So, to compute for the t of n over 2, we can replace itong part na to by something na dumiit na yung input natin. Instead of n, we have n over 2, and then we can have n over 2 over 2. Kapag try natin simplify, that's n over 4. Okay? And so on. So parang pwede natin siyang i-replace ng i-replace. Ano yung reason bakit biglang naging C of n yung part na to? Ang reason is because this is the running time for merge. Kasi the running time of solving the merge sort is the running time of merge sort is the running time of sorting the first half and the second half plus the running time of merging the two. So, ganito rin yung nangyayari dito sa each sub-tree. The running time of computing of merge sort with an input na n over 2 ay running time of merge sort na ang total number of elements na lang na i-merge is n over 2 kasi n over 2 elements na lang. And the running time of sorting yung kalahati ng n over 2, which is n over 4 and n over 4. And so on, hanggang sa makarating tayo sa base case na ang nasa babang denominator is actually equal to n. Okay? So, kapag c times n over n, we have only c or something that is in theta 1 or constant time. So if we have a recursion tree, the running time of an algorithm is just the count of all the elements here. Kasi lahat ito ay pwede nang mabilang. And we can count this by checking the height of the tree and checking the total number of leaves. Okay? So, first is, what's the height of the tree? Ginawa ko dito is I represented it by checking yung, ano ba yung height ng tree? So, this is height 0, this is height 1, etc. hanggang sa baba in each, no? And yung nangyayari sa formula ko is that I have n over 1, that's n. I have n over 2, n over 4, and so on, hanggang n over n. I can represent it using the height of the tree by getting this parang representation. N is actually 2 to the I, where I is the parang height, the current level. Kapag nakarating ako sa baba, that's 2 to the H. So, unknown sa akin ano yung height ng tree, right? So, to get the height of the tree, it's just a matter of getting ano ba yung height ng tree if my 2 to the H is equal to N. So, N is equal to 2 to the H, then solving H with respect to N, kailangan ko lang siyang i-logarithm base 2 to get log N. So, yun yung reason bakit nasasabi natin that the height of the tree is log N. We can have more examples na ganito sa next lecture natin. Okay? Kasi sometimes hindi siya divided by 2 lang, divided by 4, ganyan, and so on. Pwedeng nag-decrease by 1. So, makikita natin yung iba't ibang heights ng recursion tree. Okay? So, settled na tayo siguro dito sa log N na height. What we can do next is to check ano ba yung sum per level ng tree. This is N. Cn over 2 plus C times N over 2 is Cn. We have Cn hanggang sa makarating tayo sa baba. Okay? This is actually theta of N na in Cn din. Because this function is in theta of this g of N na N. Okay? So, ang bibilangin natin is this one, Cn, at ilang beses yan na umuulit. Ilang beses yan umuulit is the height of the tree. So, ang total yan is we have n times log n, the height of the tree. Okay? Kaya ang naging running time ng merge sort is n log n. Okay? So, what is n log n compared sa insertion sort? N log n is better with respect to running time and because it grows more slowly compared to n squared. So, paano mo compute yun? Let's say you plot itong dalawang formula na to. Given the same value for n, mas mababa yung running time ng merge sort compared sa insertion sort. Therefore, a merge sort is asymptotically better compared to the insertion sort in the worst case. Okay? So, nawala yung part. May summary pa ako dito eh. Pero yung idea is that we now identified parang 2 possible algorithms. One na ang running time is n squared at ang type ng algorithm is an iterative algorithm for the problem na sorting. And we have another algorithm, merge sort, na ang form is recursive. So the way how we can compute, one way of computing the running time of a recursive algorithm is using recursion trees. So we have one iterative, one recursive algorithm. We identified its theta of something, so it's asymptotic running time. And we can say that one algorithm is better than the other compared with respect to this metric. So, meron tayong a little bit of idea what is an asymptotic analysis for these 2 kinds of problem. Later on, mas magiging malinaw how we can compute for the running time of different algorithms because we will show more examples.